The next type of circular motion we're going to look at is circular motion in vertical loops. So here's an example. This is like a roller coaster, and a lot of physics goes into the design of roller coasters to make them fun and exciting. And one of the common things you'll see in a circular loop question is, what is the minimum velocity that the object can go at the top of the loop? A common example of this, and something that you could try at home, is half filling a bucket with water and then spinning it around over your head, and seeing how slow you can go around over your head before the water drops out on you. So let's think about the forces that are acting in this circle. So at the top of this vertical loop, there is the weight force acting downwards. And at the very top of the loop, this force is towards the center of the circle, which would be in the same direction as the centripetal force. I'm just going to come over here to these diagrams to think more about those forces. So at a velocity greater than what's called the minimum velocity, and we'll talk more about what that means later on, we have the weight force acting downwards on the cart, as well as the force on the cart from the track. So there must be some sort of other force acting downwards also. So this is the reaction force. And since both of these forces are acting towards the center of the circle, they provide the centripetal force. And just like in the banked corners and conical pendulum scenario, we can find the size of the centripetal force by adding these two together. If we have the weight force and we add to it the reaction force, then the centripetal force is the sum, or the total, of those two forces. So this is the type of question you're often asked is, okay, what's the minimum velocity that this car could be going at the top? And the minimum velocity occurs when no reaction force from the surface is required. If the car goes slower and slower and slower, when is there no reaction force required? mv squared over r. So as the car goes slower and slower, as this becomes slower and slower, the centripetal force becomes smaller and smaller. And the minimum velocity is when the only force acting is the weight force. So there's no reaction force required. Which means, if we do a diagram similar to this one here, if we have the weight force, that is the only force providing the centripetal force. Okay, so at the minimum velocity, F weight equals Fc. At any velocity greater than the minimum velocity, Fc is equal to F weight plus F reaction. There is some sort of reaction force. Down here, there is no reaction force. All of the centripetal force is provided by the weight force. And this is pretty exciting. If you're on a roller coaster, this means you feel weightless at the top, because you are accelerating downwards as if you were falling. So, and if you do go at a velocity lower than the minimum velocity, that means you'll fall off the loop. The weight force is greater than this, the force required to travel in a circle, which means you'll accelerate downwards, which isn't a good thing if you're on a roller coaster. So this is the direction of the velocity of the cart. Yeah, and at the top, this is how you can work out the minimum velocity. So over here, we can just replace Fc with mg. Then we equate the two. Remember, this equation here is given to you. Then we can simplify this down here, and then we can rearrange to make v the subject, and we get the square root of gr. Okay, so the minimum velocity occurs when the centripetal force is provided only by the weight force, and it is equal to the square root of g times r, which is the radius of the circle, technically to the centre of mass. And then another question that comes from this is, okay, if that's the minimum velocity at the top, what will be the final velocity or the maximum velocity of the cart at the bottom? So up here, this is the minimum velocity. Try and squeak that in there for you. And down the bottom here is the maximum velocity. So here there must be some sort of centripetal force acting towards the centre of the circle. I can draw this here as well. And here, because the cart is going at a faster velocity at the bottom, there must be a greater centripetal force. The weight force is still acting vertically downwards, and it will still be the same size because the mass of the cart hasn't changed. Which means the reaction force must be very big in this scenario. So remember, the weight force and the reaction force must add to give us the centripetal force, that is the total or the net force, the resultant force. So the reaction force must be very big. So the force diagram would look something like this. We have the weight force acting downwards. We have the reaction force acting upwards to provide some sort of centripetal force here, which is the sum of the two forces, of the weight force, this one, and the reaction force. Okay, so if we add these two together, we get the centripetal force. Okay, so what do we use to work out this maximum velocity? Well, this now becomes an energy problem. So up here, the car has some sort of total energy, and that is equal to the kinetic energy of the car, because it's moving, plus the gravitational potential energy of the car, because it's at a certain height from here. And down the bottom here, the total energy is going to be the same. So this is an energy conservation problem. But this time, because it's at the ground level, it doesn't have any gravitational potential energy, it's only got kinetic energy. Okay, so this extra gravitational potential energy down up here has been converted into kinetic energy down the bottom here. Alright.